Ujjwal, you are there?
Yes, ma'am.
Ujjwal, what is going on in your MD2 practicals?
Ma'am, first we did that tensile test and then fatigue test and then magnetic properties inspection. That three we did.
Okay. Okay. So 3 practicals are done till now.
Yes, ma'am.
Okay. Tiwari sir? Hello.
Yes, ma'am.
Tiwari sir, tutorial mein what are we doing?
Ma'am, till now we completed up to warm gear,
Okay.
and next time we will start for this belt drive.
Belt drive. Okay.
Yes.
Flat
Because
belt is
initially we just gave the numericals regarding the basics of the like fatigue loading or whatever they did in the machine design one and strength of material.
okay.
And once we started gear, then only I started the gear numerical.
Okay. So they have done some practice on spur gear, helical gear, worm and worm wheel, everything, right?
Yes, ma'am.
Because we are taking very little numericals in class.
Yes, ma'am.
So you can take one question and you can give 2 more questions as their assignment, so they can continue to practice.
Okay, ma'am. I will do.
Yeah. Okay, so we are done with.
Questions. Two questions for each type of gears, or one question like
Yeah,
in
2
assignment.
questions each. One we can get it solved in the tutorial class, and 2 more questions for their practice.
Okay.
Yeah. Well, we'll start our discussion on V belt drive. We have discussed flat belt drive. We have designed a flat belt with its pulley, and now we have to think about how can we transmit more power, or how can we increase the power transmission capacity. Flat belt has certain limitations because of which it cannot transmit higher power. It cannot transmit power at a larger velocity ratio. So if we want to increase the power transmission capacity, if we want to reduce the slip, and if we want to increase the velocity ratio, then we have to have another option, and that option is this V belt. So the V belt, because of its shape, if I draw this is a V belt pulley. Which has a wedge shape slot. This is the belt. This wedge angle is taken as alpha. The normal reaction is N. And here these two surfaces are now the frictional surfaces. Since it is coming in contact only with the sides of this wedge, not at the bottom. So there is always a clearance between the lower surface of the belt and this lower surface of the wedge. So it is effectively these two surfaces which are coming in contact. And so this force Fn is acting at an angle half of the wedge angle, alpha by 2. So there are applications like compressors. If you get to see compressors at petrol pumps, if you get to see generators, diesel generator sets, you can see there V belts are used for a smaller distance, for higher uh, power transmission capacity, and for higher velocity ratio. So essentially it is because of this wedging action that the power transmission capacity, the force which is required to transmit the power, which we call as the traction force. The traction force, which is again nothing but T1 minus T2, this increases, and with the increase in this, the power transmission capacity of the V belt also increases. This will normally operate at a smaller center distance compared to the center distance C is smaller as compared to a flat belt. So belt normally touches the sides and it is not touching the base. Now what happens is, what should be the angle alpha? If the angle alpha is small, you reduce the angle, this traction force responsible for power transmission, this increases. But you cannot have this angle very small. What would happen if this angle is only 5 degrees, 2 degrees, 4 degrees? This would become like this. And if you are placing a belt like this here, pulling this belt out of the wedge, this becomes difficult and it gets locked. So the force which is required to pull the belt out of this greave, this will be responsible for loss of power. And if more force is required here, where the area of contact is also increasing and it's like a small wedge or in a small cavity that it gets stuck up. So if you further reduce the value of alpha, then this is responsible for loss of power. If you increase the value of alpha more than 45, 50, 55, 60 degree, if this is the kind of wedge, this would become almost like a flat belt. And so normally the angle of wedge is taken at the range of 35 to 40. This wedge angle is taken as 35 to 40. So we'll see there is 34 degree, 36 degree, 38 degree, 40 degree. These wedge angles are given in the design data book also. And angle of this groove and the angle of belt, it is not the same. Although for all design purpose, for all calculation purpose, the angle alpha for this groove and the angle alpha for this belt. So this groove angle and this belt angle is slightly different. Which one would be greater, you think? This is the wedge for the belt. And then there is a groove and the pulley. So as I said, these two angles are slightly different. Which angle do you think would be smaller? Groove angle? Yes, the angle of the groove in the pulley would be smaller than the angle in the belt. So belt angle would always be little larger. Why so? Why so, Saurabh? Why this belt angle would be greater than groove angle? Inside force will fix the belt, inside belt needs to be fitted. If the belt angle is less than the groove angle, this entire belt will go and touch the bottom of the groove. And to maintain the clearance, we want this belt angle to be slightly greater than the groove angle. And only this would ensure there is a clearance. This would ensure that this lower surface of belt is not coming in contact with the lower surface of the pulley. So we want this friction to be only in these two sides. That is the reason why belt angle is greater than the groove angle. So if this is 38 degrees, this would be 36 degrees. If this is 40 degrees, this would be 38 degrees. This is practically, this is what exactly is happening. But for all design calculations, if we are assuming groove angle as 40, we assume the belt angle is 40 and groove angle is also 40. Like for the shaft and the bore, we are taking the shaft diameter same as the bore diameter. But at the time of actual manufacturing, some tolerance is given, which we are not considering at the time of calculation. So theoretically, we are not considering, but at the time of calculation, you see, you have some tolerances. So that is the difference between theory and practical. So this is again another question which might be asked in your interviews, whether the belt angle is same as groove angle. What do you mean by alpha? Alpha is the angle of the belt in V belt, or it is angle of the groove? And then normally the students would answer yes, it is the same for both. But you must say theoretically it is the same, but practically the belt angle has to be little greater than groove angle to maintain the clearance. Well, so this is showing an assembly of a V belt for a shorter distance. Instead of having a very long belt, we take number of belts, we increase the number of belt, and a pulley would be something like this. You can see this is a small pulley, and so this is a web pulley. This is not a solid pulley. This is not an armed pulley. This is a web pulley having 1, 2, 3, 4 grooves corresponding to 4 V belts here. So these are the grooves and this is the V belt. So there are 4 number of belts. We'll be calculating how many number of belts are required for transmitting the given range of power. Now what happens with the angle of overlap? This is T1 upon T2, which is equal to e raised to mu dash theta, where what is mu dash? What is mu dash? Yes, please. What do you mean by mu dash here? It is mu upon sine alpha or sine alpha by 2. Sarthak? It is half of the groove angle. So if you are taking the groove angle as 2 alpha, then this formula is mu dash upon sine alpha. If you are taking the groove angle as alpha, this is semi-groove angle. Now, since the value of alpha is small, you understand that this sine alpha would be small. And because denominator is small, mu dash value is greater. And since you have higher value of mu dash, for the same ratio, to maintain the same ratio of T1 by T2, you can compromise or you can have a smaller angle of contact as compared to a V belt. Or in other words, we can say that for the same angle of contact, this T1 by T2 ratio would be higher for V belt as compared to flat belt because now mu dash is greater. So for same angle of theta, this T1 by T2 for V belt will be greater than T1 by T2 for flat belt because this mu dash value is greater than V. This is how a V belt looks like. Different designs of V belt. There is a layer of cord, a rubber cord, then there is a layer of cord which can withstand the tensile forces. Below this, you have material which can withstand little compression and bending. These layers, they are adhered to each other using some adhesive or gums. Different designs, different types. This is the flat bottom surface. This is the bottom surface having notches, again covered with cord. So this is the construction of V belt depending upon what is the application or where it is used exactly. So why we are worrying about this T1 by T2 for V belt and flat belt is we are trying to work out why the power transmission capacity in V belt is increasing. So as I said, for the same value of theta for flat belt and V belt, since mu dash is greater than mu, T1 by T2 in case of V belt, this is higher. And if we take this ratio as K, we know that the power transmission capacity, this is T1 into K minus 1 by K to Vp. Since this value of K is higher for V belt, the power transmission capacity also increases. So with the increase in this ratio of T1 by T2, the power transmission capacity also increases. And what about the center distance? Suppose we want to have the same value of K, that is T1 by T2. For the increase in the mu dash, since mu dash is increased, theta can go down. And what is the relation between theta and the center distance? Pi minus d2 minus d1 by c. So what is the effect of smaller theta on center distance, or what is the effect of center distance on theta? If the value of c is less, if the value of c is small, this term becomes larger because this is denominator, and if this term is larger, then because this is negative, theta will again go down. So for smaller value of theta, the center distance goes down, or for smaller value of center distance, theta goes down. Since flat belt is effective only for longer distance, for larger value of C, if you have to transmit power in a small distance like in generator or compressor, flat belt efficiency goes down. Because the efficiency of flat belt goes down, we are using the V belt over there. And for the smaller center distance, because we have to transmit it effectively, we have to reduce this theta. And we are reducing the value of theta and we are increasing the value of mu because it is mu dash now. So the power transmission capacity would not be compromised. And all this is another reason why we are replacing flat belt with V belt. Many a times efficiency is little lower for V belt as compared to flat belt. But yes, with improvement in the material, then that can be worked out. And if we talk about the velocity ratio, I told you normally velocity ratio for flat belt is in what range? What is the range of velocity ratio for flat belt? 4 to 10 till 10? No, it's too high. Velocity ratio is limited to 3 to 4. Not more than that. But with V belt, we can go up to 7. This can be 6 is to 1, 7 is to 1 for V belt. Normally for flat belt, the velocity ratio would be limited to 2.53, not more than that. We have solved the problem from 1000 RPM to 300 RPM, that is the reduction in the velocity. So that is the most preferred value of velocity ratio that is considered. Another advantage of V belt over flat belt is this can be comfortably used for vertical belt arrangement or for inclined arrangement. If the two pulleys are placed one over other, normally a flat belt won't work here because this will become slack here under the action of gravity. The pulley will become slack here and the initial tension would reduce and the power will not be in a position to transfer. But with V belt, this vertical arrangement is possible. So that is another advantage because this is working more like a positive drive. It is like a positive engagement due to the groove. We have to consider what is the effect of inclination, and that part we'll see while selecting a belt drive. What about the initial tension? What do you think would be the initial tension for V belt, less than or greater than flat belt? Initial tension required to transmit power. Yes. Ayush, Sarvesh. Sarvesh, Jaswant. These two boys, they are never there in the class. Jaswant. Are you there? Initial tension required would be more for V belt as compared to flat belt. Ayush?
Yes, ma'am, I think.
Yes. Jaswant, what do you say? Jaswant? Yes, it would be greater. Bhavesh? Initial tension would be less than or greater than initial tension in the flat belt. Karthik? Karthik? Initial tension in V belt is less than the initial tension in the flat belt because this is like a positive engagement. So this is not exactly similar, but it is quite close to a gear drive. So it is engagement between the groove of the belt and the belt itself, the groove of the pulley and the belt itself. And hence, even with lesser initial tension, this can start transmitting power. Unlike a flat belt, if the initial tension is reduced to zero in flat belt, it will not start transmitting power. And so the required initial tension for V belt is always less than flat belt. We'll talk about chain drive where this initial tension is not required at all. What about slip? Slip in V belt? Yeah, so it is theoretically it is out of question. There should not be a slip, but then yes, it is less. So if we are considering 2% slip in the flat belt, we considered 1% slip or 0.75% slip here. Then how do you designate a flat belt? Oh, sorry, a V belt. Normally, V belts are not designed. V belts are selected. So selected because there are standard V belts available. We have V belts available. Before we go for designation, we'll talk about the type of V belt. So there are 5 different grades of V belts available. A, B, C, D and E type of flat belt. As we move from A to D, the cross section is increasing. Do you have design data book? Please open the design data book. It's given on page number page number 160, table 15.8. Yeah, Pradyuman is asking if initial tension is average of tight and slack side tension, why it should be higher than the flat belt. Then it should be higher. Listen, in that particular calculation, we are trying to establish a correlation between initial tension and belt tension. So there is some initial tension Ti. As the belt starts rotating over the pulley, the initial tension increases on the tight side and it reduces on the slack side. So it is from Ti, that it is Ti plus del T by 2 and Ti minus del T by 2, that the tight side tension and slack side tension, they start building. And without initial tension, a flat belt cannot work. But in case of V belt, because of the groove, because of the positive engagement, this initial tension required is less. So we'll see what is the effect of initial tension here in case of V belt drive. So that part we are again coming to it. But basically you have to understand that this initial tension is not required because of this positive engagement. Is that okay, Pradyumna? No. So initial tension in case of V belt, here the formulation or the correlation would be little different. So if this is how a V belt looks like, where this is the thickness and this is the width on the top surface. So refer the design data book. You can see from A to E, the width is increasing and the thickness is increasing. So if the belt type A looks like this, belt type B would look like this. Belt type C would again be having a larger width, larger thickness. What is the width given for belt type C in millimeters? Yeah, it's given 22. And what is the thickness given? Nominal thickness? 14, right. So as you move from A to E, the width increases from 13 to 17 to 22, 32 to 38, and thickness increases from 8 to 23. And accordingly, the dimensions of the pulley diameter that we'll be selecting, this also increases. So depending upon what is the power transmitted or the power transmission capacity, each kind of belt designation or the code ABCDE is selected for the required range of power. Now you see the range of power for A is 0.35 to 3.5 kilowatt. For B, it is 1.5 to 15, which means if you have to transmit 2 kilowatt of power, you have an option to select either A or B. For transmitting 14 kilowatt of power, you have a choice of B and C. We have to decide whether we have to go for B cross section or C cross section. So what happens is, either for transmitting say 13 kilowatt of power, we select B or C. When we select B cross section, where the suggested range of power is lying, it is 1.5 to 15. Here the number of belts required would be more. But for C type, probably you can work out with only one belt or two belt. But for B type, you might need some 4 or 5 belts. So you have to increase the number of belts for transmitting the same power. A single belt is rarely used. So normally you go with 2 belts, 3 belts, 4 belts, which we'll find out. So for the same power transmission capacity, if you are using a smaller thickness, if you are moving towards a smaller width, number of belts, this will go up. And if you are going for a larger width, number of belts will go down. So what happens with increase in number of belts? What if you have to use 7 belts or 8 belts instead of 3 belts? What happens with more number of belts? Vaishnavi? Manufacturing cost increases, okay. What else? If one fails, other are affected. Look at this particular image. Here you can see the number of belts are 4. Power distribution is not uniform, no. This is the clue here. Can you give me the answer looking at this image? More area, yes. Pulley design, yes. So if you have 7 belts, you should have 7 grooves in the pulley, which means this space, the space between the 2 belt has to be there, a minimum space. So width of the pulley increases, you are right. And as the width of the pulley increases, its weight increases, then the shaft has to be stronger to withstand this much width or this much size of the pulley. Again, ultimately, the load on the bearing increases and the cost of the drive increases. And but there is an advantage with a smaller belt also. Smaller the belt, smaller the size of the belt, longer would be the life. But with larger cross section belt, the life also goes down. So you have to always compromise between whether you are going to have a B type of belt or C type of the belt. So in first problem, we'll try to solve a problem using both. So say half of the class will solve it for B type and other half will solve it for C type, so that we have a good comparison, or you would get a fair idea what is the advantage and limitation of using a smaller cross section belt over a larger cross section belt. And that will help you to design what is the most optimum design. Most optimum design. So the smaller belt will ensure there's a longer life. And what happens if out of 4 belt, if one belt undergoes wear and tear, what would happen? If one of them is worn out, so with wear and tear, yes, with wear and tear, its length would increase, and you cannot replace a single belt. You have to replace all the belts. So all the belts, even if one fails, it calls for replacement of all the belts, and so also the cost increases. If you replace only one and one of the belt is new and other 3 belts are old, then the power which is distributed is not uniform. The force which the belts are withstanding or which they are transferring, this is not the same. Now, while we design, we'll refer to the design data book. This is the length at the nominal or at the neutral axis. This would be the length of the belt at the inner surface, and when you are measuring here, this would be the length of the belt at the outer surface. So this, when you are measuring, I'm drawing a slightly exaggerated view. This is the belt drive with this given thickness. This would be the inner length, and then there is a nominal length which is passing through its neutral axis. So a V belt is always designated with the type of belt. It is either A, B, C or D, and some number, say 3421. So this 3421 is its inner length in millimeters. And this first alphabet, this is telling us about what is the width and the thickness. So if it is a B3421, it has to be replaced with B3421 only. And the standard inner lengths, they are also available. So while designing a V belt, or if you are selecting a V belt, all you have to do is you have to find out how many belts are required, what length and what cross section is required for transmitting this much amount of power. If you talk about efficiency, the efficiency of V belt is actually less than the efficiency of the flat belt. So when efficiency is not too much of an issue, it is more about the power transmission capacity, we go with the flat belt drive. Cost, we have already seen the cost of the V belt would be higher than the flat belt. We have to consider the bending loads here, the bending forces or the bending stresses in case of V belt. Now, since the length of the belt is less and it will be bending more frequently as compared to a flat belt. What about the peripheral velocity? Which one would have higher peripheral velocity, flat belt or V belt? Which one would have a higher peripheral velocity? Manan? Kaustubh?
V-belt.
V belt. What is the value of assumed value of VP for flat belt for better life? We had assumed some value from the data book. It is 1000 meter per minute. Here for V belt, you can go up to 1500 to 1800 meter per minute because there is no problem of slippage. So this is another reason why the power transmission capacity increases, because PR is now T1 minus T2 into VP. So since you can afford to have a higher value of VP, so also the power transmission capacity increases. Again, comparing the power transmission capacity of the V belt and the flat belt. We know that T1 by T2 for V belt is e raised to mu dash theta, and for flat belt it is e raised to mu theta. So it is seen that the power transmission capacity for V belt as compared to the flat belt, this is also roughly in the range of 1 upon sine alpha by 2. And this value comes out to be almost 3.5 times. Let's see how it comes out to be 3.5 times. Assuming the value of alpha as 34 degrees and the value of alpha as 40 degrees, what would be the ratio of this PV by PF? What will be PV by PF if this is 34? And this ratio if this is 40? Yes. .42 for 34 degrees and 2.9 for 40 degrees. So you see, you increase the groove angle and this ratio would go down. You decrease the groove angle and this ratio would go down. So why not go with 30 degrees? What if you go with 30-degree groove angle or 25-degree groove angle? This ratio would further increase. But at the cost of what? At the cost of what? Yes. Yeah. So it is a loss of power because then the power is required to pull the belt out of that wedge. It will get locked over there. So here, although theoretically this with smaller value of alpha, the flat belt and V belt is showing a higher ratio, but this is again theoretical. In practical purpose, in theory, we are not calculating what is the loss of the power. We are not calculating what is the force required to pull it out of the wedge or the sheave. But practically, it is seen that there is loss of power with the decrease in the angle alpha. So these are some of the practical terms which you would not find from theory. So if you are simply learning the theory, you will never get these kind of answers. So why the value of alpha is around 40 degrees or 38 degrees? So this is the reason. Because we have to make sure that the power transmission capacity increases or the power loss goes down. Okay, normal value of mu is 0.35. If I am going with alpha as 34 degrees, what is my mu dash? Mu dash value? Mu upon sine alpha by 2. What is mu dash? (1.19). Is it possible to have coefficient of friction 1.19? Ayush? Can you have coefficient of friction greater than 1? Yes or no? Anyone? So it is practically impossible to have a coefficient of friction greater than 1. This is impossible. So this mu dash, this is just a term. It is just a concept. And because of this sine alpha by 2, the coefficient of friction effectively increases. It doesn't mean that the V belt has a coefficient of friction greater than 1. Are you getting me? Because this value of mu, this entirely depends upon the two materials, the material of the pulley and the material of the belt. It doesn't depend upon the groove angle. Do you agree with me? Are you there with me? So since this is only dependent upon the material, you can never have the value of mu greater than 1. So this mu dash coming out to be 1.9, 1.19 is this modification since two surfaces of the wedge, two side surfaces of the wedge, they are active and the normal force is getting transmitted to these two surfaces. That is the reason why this effective coefficient of friction is coming out to be greater than 1. So you have to keep in mind this effective coefficient of friction is just a term. It's not the value. It is not defining the value of coefficient of friction because theoretically we can never have a material whose coefficient of friction is greater than 1. Then while calculating what is the power transmission capacity or the rated power, we are only considering the tight side tension. We are only considering tight side tension and the centrifugal tension in case of flat bed. But in case of V belt, we have to consider its load carrying capacity, which is T1. T1 depends upon its material and its cross section area minus its centrifugal tension minus what? The tension due to bending into Vp. So this T1 is also written as Fs. For V-belt design, we'll be referring to Shivalkar data book and PSD design data book. So next class, Saturday, we'll be solving a problem on belt drive, V-belt drive. I want you to be ready with both the design data books. Both the design data book will have little variation, but we'll try to solve the problem and ultimately the answer would come out to be same. The final answer would come out to be same. Some data is given in BSD data book, which is not given in this Shivalkar data book, only for V-belt drive. So the chain drive and V-belt drive bearing design will be referring PSD data book. So I'm reminding you again, next class, please be prepared with both the design data book. So T1, the belt tension is responsible for the load carrying capacity. FC or TC. In other books, you would see TC as FC, the centrifugal tension or the centrifugal force. This depends upon the peripheral velocity. You go on increasing the peripheral velocity and the value of FC would increase. So even if we are saying that this works at a higher peripheral velocity, maybe 1300 to 1800 meter per minute, but with that, the value of TC would increase. And since this is a negative term, the value of PR will go down. So this VP is responsible for increasing this PR, but because of VP, you know that this TC will have rho V square component. So there is a V square component which is responsible for reducing the power. And hence there has to be a golden mean how much you can increase the peripheral velocity to achieve the required PR, to achieve the required power transmission capacity. And this TP, the bending tension, also referred as FB in PSD design data book. This would depend upon the diameter of the pulley. The pulley diameters D1 and D2. Which one is preferred? To reduce the bending stress, the diameter of the pulley should be small or large? Tanvi? A large diameter would reduce the wrapping radius and so it will reduce the bending stress. If you are picking up a smaller diameter pulley, then this FB value increases. And so we always prefer a larger diameter pulley to reduce the bending stress. So the belt will not be undergoing those bends as severe in for a smaller pulley. So the severity of bend would be more in smaller diameter pulleys. Then there are certain correction factors which we have to take into account. So this formula with number of experiments that are carried out, this formula is finally based on the lab conditions. And the lab conditions say that theta should be 180 degrees. When can you have theta 180 degrees? The table that we are referring for A, B, C, D, what is the power transmission capacity, what is the width of the belt, what is the thickness of the belt. So those dimensions, they are calculated from experimentation which was performed in the lab condition, which says that theta should be 180 degree. What do you mean by theta 180 degree? When can you have theta 180 degree? Yes, when the velocity ratio is 1 or when the diameters are same. Which is rarely the case because either you want to reduce the RPM or you want to increase the RPM. And so there is a correction for this variation in the diameter. Or we have to consider the equivalent small pulley diameter factor. Another condition is the length of the belt correction. Length of the belt. So the design data book by PSG will be giving us the length of the belt for given cross section for given power transmission, which might need some correction. So that correction is required because the belt has to undergo bending, and so the inner length and the outer length will not be same. There would be a variation because of change in the center distance also. So this also needs correction. And the third condition in the lab is there are no shocks. But shock is always there, and so we have to take into account the service condition or the service factor. So next class, are you tired now? Should we continue for next 10 minutes? I know this question is illogical. Nobody is going to tell me that we can continue. Saurabh? Satyacharan has immediately left the meeting. Is it okay if I continue for 10 minutes more or should we stop here? It depends upon your level of fatigue.
Ma'am, it will be better if you take doubts regarding
If we take the doubts.
today's discussion.
Okay. Okay, so next class we'll talk about what are the correction factors because actual conditions are not similar to lab conditions. So actual conditions are different, and so we have various correction factors which are required while designing. So we'll discuss about correction factors, and in next class we'll solve a problem on V-belt design. We'll solve one problem by Shivankar and one problem by PSD design data book. Okay, now you're free to ask questions related to whatever we have discussed till now. Yes, please. Saurabh, you have any doubts?
Yes, ma'am. I have a doubt that why efficiency of V belt is less than flat belt. It is not clear.
Why efficiency is less? Okay. So actual condition, there are more number of losses. When we say here the friction is helping us in transmission of power, although it is helping, but it is also leading to wear and tear. Wear and tear here is high, the cost is high. So overall, when we talk about efficiency, it is not only about the power, it is the cost wise also. And other things that we discussed about the belt drive. The
Ma'am, but we
flexibility of V belt also goes down. Here we lose power because of the bending stress also. Due to its thickness, you have seen the thickness, its cross section is trapezium. Because of this trapezoidal cross section, this thickness has to be more than the flat belt. Because of which there is a layer below the neutral axis and a layer above the neutral axis which is undergoing tension and compression. And this leads to more bending losses due to force and more bending stress induced in the belt, which reduces the power transmission capacity. So either you can increase or maintain the efficiency, or you can increase the power transmission capacity with loss in efficiency. So it is again performed by the experiments that they have come out with lower frequency for as compared to the flat belt, although the power transmission capacity is higher. Yeah, what's your question? What was your point, Saurabh?
Define belt efficiency for new or after some revolution.
Yeah, so as you understand, with service, with operation, the efficiency will further go down. Normally, the rated efficiency and the rated power is for new belt, but it is always designed for the worst scenario. So at the time of design, we assume that this is designed for the value PD, which is taking into account the service condition. But yes, with time, it will have certain life. It will have those many number of cycles after which it should be replaced. So you replace a belt with a belt of similar designation. Again, we are saying that the peripheral velocity here can be higher than the flat belt. We are increasing the value of peripheral velocity, assuming that this would increase the power transmission capacity. And then there is no slip. And so also you can increase it beyond 1000 meter per minute. But then the centrifugal tension is coming into picture. So you cannot increase VP beyond that range. So the moment you increase that, the value of PR goes down. Because that is a negative term or an undesirable force coming into picture. So these days, with improvement in the material, in lot of research in the material science, there are few companies who are coming up with flat belt with a better power transmission capacity, with better efficiency. And so they are improving the material so that with flat belt, with a simpler design, with a low cost, you get almost the same power transmission capacity with a better efficiency as compared to V belt. So you can search on net for new materials that are used in flat belt. We studied about this chrome tanned leather belt. So it was not the conventional leather belt. It is the belt which is having a chrome layer or a chrome covering, or it is tanned with chrome. So likewise, new generation materials are coming, which helps in improving all these factors, reducing the losses. What else? Arshil,
Yes, ma'am.
any doubts?
No, ma'am. It's fine.
Yash, Shivesh,
Yes, ma'am. No doubts.
Yes, ma'am, no doubts.
were you really attentive throughout the class? And you still have no doubts? Utkarsh?
Yes, ma'am.
Okay, there are two Utkarsh. 13
Yes,
and 12. Who is answering? 13. 113. Utkarsh, all clear?
Yes, ma'am.
Strange, huh? Okay. Thank you. So we stop here for the day. Saturday, we'll discuss the correction factors. We'll solve the problem. Please keep your PhD design data book and Shivalka design data book. Both the books handy with you. Thank you.